In this video, we're going to be dealing with finding equations of lines in three-dimensional space. I'm mostly going to focus on parametric, but do a little bit of the symmetric equations as well here. I guess also I should say when I say parametric, sometimes it's really vector, depending on exactly how it's written down. I kind of view them as basically the same thing. Let's start off with some problems here. So the first one here, I want to find parametric and symmetric equations for each of the following lines. So part A is the line through the point, -1, 5, 0. That is parallel to, or maybe in the direction of, the vector 2, 3, -2. So the general setup here for our lines, when we do a parametric setup, is we are going to get a line equation that looks like r of t, so a vector r. And what this is going to be is it's going to be our point. Now I'm going to write this as a vector just to sort of be consistent here. It's a little confusing occasionally. A bit better. Let's try that again. 1, 5, 0. And then what I'm going to do is add t times the vector. So it's the point plus t times the vector. And what we're thinking of here is that there's some point in space, so some point over here, and then our vector, maybe we'll draw in green here, let's do a different green. So our vector here is in green, and this might be the point plus 1 times the vector. And then you can add another copy of that vector, ugly, but the point plus 2 times the vector. You could even do the point with t equal -1, the point sort of minus the vector. Or you could do the point plus half of the vector. Or maybe that's more like a third the way I've drawn it. But you could do whatever multiple of that vector you want added to the point. And if you think about what that creates, that's a line. And so that's generally our setup here, is it's just r of t, our parametric equation for the line, or maybe you'd call this a vector equation for the line. It's the point plus t times a vector in the direction of the line. And often we might sort of combine these as -1, 5, 0, plus we could distribute the t, 2t, 3t, -2t, and then you could add the vectors component-wise and get -1 plus 2t, 5 plus 3t, and then 0, which I don't need to write, -2t, and this is for all t. So I'm just going to rewrite my r of t equals that. And this is really the vector equation. I would really think of it as parametric, but oftentimes people make a slight distinction here and think of the parametric equations, not equation, but really equations, just the x equals the first component. That's -1 plus 2t. Y equals the second component, 5 plus 3t. And z equals the third component, that's the -2t. I don't really get that concerned about the difference between parametric equations and vector equation, because essentially they're just two different ways of writing the same thing down. I guess parametric equations, you don't really have a vector explicitly there. I would really think of this vector equation is sort of a parametric equation as well, but that's the case. Symmetric is going to look a bit different. Pick out an orange here. So the symmetric equations, what we're going to do is we're really going to write x minus, well, the x coordinate of the point, that's -1, and then we're going to divide by 2. And then we're going to get y minus 5, so that's y minus the y coordinate of the point, and then we're going to divide by the sort of y component of the vector. And then we'll get a z minus 0 divided by the z component of the vector, that's -2. So these were the symmetric equations. So these do look a little bit different. We don't use these all that much in this course, but probably mostly deal with the parametric, but they're there. And this you could, of course, rewrite as, if you want, x plus 1 over 2 equals y minus 5 over 3 equals z over -2. let's take a look at maybe a better drawing of this in Mathematica of the line here, so we get an idea of we have our point plus multiples of the vector. So for my crude drawing in Mathematica, oops, not the thing we want, we'll get to that later. Here's really the drawing. So this green point here, that's the point on our line. Don't have this really in, like, coordinate-wised out very well, but that's okay. This red is the vector, and then the blue is the line. So we can actually rotate this around, and you can see sort of the blue scape, go all the way there, sort of appear. That line would extend forever. It's really point plus some multiple of the vector. The vector really sort of on the line or in the direction of the line or parallel to the line, whatever terminology you want to use. Next question, we want to do the line through a point and parallel to this vector. Same setup as before. So the vector equation is going to be really r of t. It's going to be, I'm going to think of the point really as a vector 3, negative 2, 4 plus t times the vector 0, negative 2, negative 3. So point plus t times the vector, or just the point plus multiples of the vector, scalar multiples of the vector. And you might rewrite this as 3 plus 0t, which is just 0, negative 2 minus 2t, and then 4 minus 3t. So there's really your vector equation or your parametric equation in this thing here. The symmetric equations, those are going to be, x minus 3. I take x minus the x coordinate, and I'm going to divide by the, well, I run into trouble here. I want to divide by 0. So we can't really divide by 0, so that creates a certain amount of problem when we try to do the symmetric equations. We actually don't want this here. What we're going to do is we're just going to say, well, x has to be fixed at 3. So x is 3, and then we'll get the symmetric equations like above here, a little bit, so above up here, with just the y and z, so one equation. So then when I continue this, I'm going to get a y minus negative 2, that's y plus 2, divided by negative 2, and then I get a z minus the z coordinate of the point, which is 4, divided by negative 3. So this whole thing here is the symmetric equations, although I suppose there's just one equation. Well, there's two equations. There's this equation, and then the equation x equals 3. Before we had sort of, well, two pairs of equations that are linked. Maybe that's 3 equations if you think about the first one equals the third. Yeah, but these are the symmetric equations. And the picture, if we looked at Mathematica, would look very much the same. So what we get here, and we go down here, here's the picture. You've got a point, you've got a blue line, so the point is green, you've got the line in blue, the vector's red, this is just one multiple of the vector, and you could keep doing 2 times the vector, or half of the vector would give you all of the points on the line, or the point plus 0 times the vector would be at the point. Here. Okay. Type of problem that looks a little bit different. We're going to find the line through 2 points. So before we were given a point and a vector, so we don't have the vector, we're going to have to create that. So what we're going to do here is we need a point and a vector. So my point that I'm going to use on the line, I'm just going to use the point 2, 0, 4. I'm going to sort of arbitrarily choose the first point. You could use negative 2, negative 6, 8, and that would work just as well. Now my vector, I'm going to say in the direction of the line. Well, that's going to be the vector. That's the difference between these 2 points. So I'm going to take negative 2, negative 6, 8, and I'm going to subtract 2, 0, 4. You could do the subtraction in the other order. It would not matter. Well, you get a different parameterization, but it'd be the same line. Negative 2 minus 2, that's negative 4. Negative 6 minus 0 is negative 6. 8 minus 4, that's 4. So I get negative 4, negative 6, 4. And then when I do my parametric equation, I get r of t is, okay, my point is 2. I'm going to write it this way. I get a 0. I get a 4, and I'm going to do t times my vector, so it's 2 minus 4t, 0 minus 6t, and then 4 plus 4t. So I kind of skipped some steps there and combined those just to go a little bit quicker there. The symmetric, I have a point and a vector, so the symmetric equations are going to be x minus the x coordinate is 2, divided by the x component of the vector is -4, and I get y minus 0, which is just y, divided by the y component of the vector is -6, and then I get z minus the z component of the point is 4, divided by the z component of the vector is 4. So those would be my symmetric equations. We should make a note here that in this case, both for the symmetric and the parametric, or the vector form, if you look at this vector, you can divide each component by 2 here. So this vector here, whoops. When we look at it, that vector really equals 2 times -2, -3, 2. Now you could pull out a negative as well, but then you get 2 positive and a negative component. What that means is you could have, if you wanted to, said, well, I'm not going to use the vector -4, -6, 4. I'm going to use the vector -2, 3, -2. And if you do that, all that's going to happen is this 4 is going to get replaced by 2. That 6 gets replaced by 3. And the 4 multiplied by the t gets replaced by a 2. Now that gives me a somewhat different parameterization, but the same one. Essentially what I'm doing is replacing my t here with 2t. So when t was 1, originally we'd get 1 times 4, and now when t is 1, well, 2, I guess, we'd get 2 times 2 is 4. So in some sense, we're just scaling the t. Likewise, if you did this divide by 2 trick with the vector, you'd get a 2 on the bottom of your symmetric, and a 3, a -3, and then a 2. So -3, -2, just to make it clear the negatives stay there. So you could do that there. We should maybe look at this one in Mathematica. Here, very similar picture, but a little bit different. Here, the blue, you have the blue line, and then you have your initial point is the green, the sort of terminal point is the brown, and then the vector, I did brown minus green to get that vector. You could also do green minus brown and just put the vector in the other direction. You get the same line, it's just what were your positive t's become your negative t's, and vice versa. You may start and end at different places, and you can get a sense when I rotate this around what's going on. We're just taking this green point plus multiples of the red vector, and all I used the brown point for was to get that vector, the red vector. Okay. One more like this one just for the sake of here. We've got 2 points when we find the line between them. So I'm going to choose my point on the line. I'm going to choose the first one, 3, -1, 4. And then my vector in the direction of the line, this is going to be, let's do the same thing, second point minus the first point, 1, 8, -2, minus 3, -1, 4. And that's going to give me the vector, let's see, 1 minus 3 is -2, 8 minus -1 is 9, -2 minus 4 is -6 here. And so my parametric equation is going to be the 3 minus 2t. So I take the points x minus 2 being the vector's sort of x component, but I have to take the vector part times t. The y part will be -1 plus 9t. The z part will be 4 plus -6 or minus 6 times t. And then for symmetric, I just get x minus 3 divided by the -2. Y minus -1 turns into a y plus 1. You get a very good plus there. Plus 1 divided by 9. And then we get a z minus 4 over -6. So those would be our symmetric equations. Okay, so that's really finding equations. So we did. And now some questions about these equations, because we want to know, are the lines from 1A and 1B parallel, skew, or intersecting? So let's go find these here. So 1A, we have this particular setup. So what I'm going to do here, let's see, can do a, let's just see if I can copy this. Let's see. I think I should be able to get all this, and then I can, let's see, I should have a copy. Let's copy that. So there's R of t. So there's the first one. And then we can edit, let's paste that. So there's our first equation. Let's click off there. So that's the first one. Now the second one, that was B. Let's copy that. Whoops, sorry, I gotta highlight it first. So let's highlight this. So with that, just get the box around it, that's okay. And then go here and paste that down. So there's our two equations. I guess I didn't get the R of t equals here. So let's do the R of t equals. Now I could call this R1 of t and R2 of t. Put a better arrow there. R of t. So just to say we have two different lines here. And now our question here, are these lines parallel, skew, or intersecting? So first thing I would check here is, are they parallel? That would mean their direction vectors are multiples of each other. So here the vectors, okay, you could go back to what we did for 1a and 1b and find the vectors we used, but you can also read this off of the parameterization. So the vector is really just the things multiplied by t here. And so what you get here is your vector in the direction of the line. It's the 2, and then the 3 there, and then the negative 2. The second one has a vector, well, there's no t there, so that's a 0. And then I get a negative 2, and then I get a negative 3. Now if you look at these two vectors, you'll notice they're not scalar multiples of each other. I can't, like if they were, for instance, I'd have to take 2 times something, give me 0. That'd have to be 2 times 0, but then 3 times 0 doesn't give me negative 2, it would give me 0 again. So I can't take 2, 3, negative 2, multiply that by some scalar, and get this vector back. That means the vectors are not parallel, which means the lines will not be parallel. So we're talking about skew or intersecting. So essentially what we need to do then is figure out, is there an intersection point between these two, the lines that have these two parameterizations? Now what you would do is you would say, well, if there was an intersection point, the x's would have to be the same, the y's would have to be the same, the z's would have to be the same. So what we're going to do is we're going to think at the R1, we're going to get negative 1 plus 2t. This is really the x. The y is 5 plus 3t. The z is negative 2t. And we want those to be the same as what we get in R2. Now there's a temptation to use the same t here, but it might be that if you plug in, say, R1 of 1, that might be the same thing as R2 of 3. So you might have to plug in one value of t here and another value of t here, which means we're going to use a variable other than t here. So how about we use, I don't know, s. So we'll get a 3 for the x, the y, negative 2 minus 2s, and then the z, 4 minus 3s. So now what we're going to do is you'll look at this and say we've got 3 equations in 2 unknowns. So this could be sort of an overdetermined system. There's the question, is there a solution or not? So I have to solve this. This particular one, what I would do is take the first equation. I can add 1 to both sides. I get 2t equals 4. That gives me t equals 2. And then I could plug that into, say, the y equation. And I get then 5 plus 3 times 2 is 6, is negative 2 minus 2s. That's going to give me, let's see, 11, 13 equals negative 2s. That gives me s is negative 13/2. Now, right now, all we used were the x equation and the y equation. So for this to actually be a solution, we have to be able to plug in our t of 2, our s of negative 13 halves, and get the z equation to be true. So let's try that. The z is negative 2 times 2. That's going to be negative 4 on the left. On the right, you get 4 minus 3 times negative 13 halves. Okay, that's not going to be negative 4. In particular, it's going to be positive. It's really 4 plus 39 halves, which is 8 halves plus 39 halves, which is 47 halves. But all we really care about is we got different things here. So what happened here is we said that if we plugged in a t and an s, where both the x's, or all of the x's, y's, and z's were the same, if I just look at the x and y equations, t would have to be 2 and s would have to be negative 13 halves. But if I use t is 2 and s is negative 13 halves, that doesn't work out for the z's. So what that means, and sort of the end here, is that these lines are skew. Here, so they're not intersecting. So picture of that. Here in Mathematica, here's these two lines, and we've got the blue line and the red line. You can kind of see here where they're sort of in space. They're certainly not parallel. They're not in the same direction. And it looks like, from this perspective that they might intersect, but that's just sort of one's on top of the other there. And if you rotate around, you'll see there really isn't an intersection point. One sort of actually goes above the other, and one passes underneath. So these are skew lines, and there should be like some distance between them here. They just do not intersect, and they're not parallel. Okay, what about the lines from 1a and 1c? Are these parallel, skew, or intersecting? I'm going to go through and grab my line from 1a. Let's get all of this. Plop that there, and then drag it down so you can see that line. Scroll down, and then let's see if we can move that up a little bit. There we go. And now let's go pull up, get the line from 1c. So you might eventually just start with the parametrization. Okay, this is a little bit messy. I think I'm going to have to rewrite this. I have 2 minus 4t, negative 6t, and 4 plus 4t. Or I could use the red numbers, but let's use the blue. 2 minus 4t, negative 6t, and 4 plus 4t. I have R2 of t is 2 minus, and I already forgot, 2 minus 4t, negative 6t. 2 minus 4t, negative 6t, and 4 plus 4t. Let's just look back up and verify that that's what that was. 4 plus 4t. Yep, so there we go for our two equations. Now, these ones, now look at this. Let's look at our vectors. So here our vector in the direction of the line. What that's going to be in this case is, again, it's the things that are multiplied by t, the coefficients of the t. So I get a 2, a 3, a negative 2. In this case, let's just call our vector v. What we get is negative 4, which is multiplied by the t, negative 6, and then a 4. Now if you look at these two vectors, it turns out if you take 2, 3, negative 2, and is sort of the direction vector for the first line, and you multiply that by negative 2, what you get is negative 4, negative 6, 4. Well, that's the direction vector for the second line. So what that means is that the direction vectors point in the same direction. They're multiples of each other. And what that means here really is that these two lines are parallel. So we have parallel lines. This is sort of the easy case because you can do that. You can check this without much calculation. And then pictorially, what that is again, there's going to be no intersection, but now these lines are, well, they're parallel, like in the plane, but you can kind of rotate around. I mean, I could, from a certain perspective, look at them, they overlap, but that's just a perspective issue here. So they're never going to intersect, but they're in the same direction. Last one. So let's do 1a and 1d. So again, let's go and highlight. I'm going to copy our 1. Paste. down there. Let's go pull off our line from 1D. That's this line here. And let's copy that. And paste down here. So we can see what's going on here. There we go. Okay, so this one, what I'm going to do, I'm going to just call this one R2 of t, put a subscript 2 on that second one just to talk about R1 and R2. So we'll do the same thing we did a couple problems ago. We're going to try and equate the x's, y's, z's. I guess before I do that, I should check, are these parallel? So my vectors here, my direction vectors, in the first one, I get the 2, 3, negative 2 that I've been using. In the second parametric equation for a line, I get negative 2, 9, negative 6. You can see these vectors are not scalar multiples of each other. I can't take 2, 3, negative 2, multiply by some scalar, by some number, and get negative 2, 9, 6. For the x components to work out, I'd have to multiply by negative 1, but 3 times negative 1 isn't 9, it's negative 3, so it just doesn't work. So these lines are not in the same direction, so they are not parallel. How do I know it's not parallel? It could be skew or intersect. So again, I'm going to equate the x's. So I get x is the negative 1 plus 2t, and then it would equal 3 minus 2t, but instead of t, I'm going to use an s here. Again, the idea is you might plug in, say, a 5 in R1, and then a 2 in R2. Here, you might plug in different t's in each equation and get the same point for each. So I'm going to use different variables. And then the y's, generally might not even write the x equals y equals, but I'm thinking that. The y is 5 plus 3t equals the y component of the second line is negative 1 plus 9, and I'm going to put an s where the t is. And then for the z's, I have a negative 2t equals 4 minus 6s. So now again, we've got 3 equations, 2 unknowns, sort of more equations than we need. The question is, can we find a solution that works for all 3? You could, I guess if you're aware of those, use matrix techniques, but we're going to sort of just solve this somewhat, somewhat roughly here without any real strategy, just kind of doing things that work out. So what I'm going to notice here is if I take the x equation and I add the z equation, the 2t and the negative 2t will cancel. So if you take this x equation plus the z equation, on the left I'm going to get negative 1 plus 2t. Whoops, let's switch to green here. Negative 1 plus 2t plus negative 2t. So take the left-hand side plus the left-hand side should equal the right-hand side, 3 minus 2s, plus the right-hand side down here, which is 4 minus 6s. And that gives me negative 1, the 2t and the negative 2t cancel. That's what I noticed was going to happen. 3 plus 4 is 7, minus 8s. Whoops. And now, let's see, I can move the 8s to the other side, the negative 1 here. That's going to give me an 8s equals 8, which tells me s has to be 1. So if I'm going to satisfy the first equation and the third equation, the x and the z, I have to have s equals 1. Now you could solve for t now. So I could take, say, the third equation, maybe looks the simplest. I get negative 2t should be 4 minus 6 times 1. So that turns into negative 2t equals negative 2. That gives me t equals 1. So here I actually got t is 1 and s is 1. Here, so they look like they're the same. Now let's check that with the y equation, which we didn't use. Here. Now actually, because I kind of do this haphazardly, I'm going to check all the x, y, and z. And to do that a little more quickly, I can just plug into R1 and to R2. So I'm just really going to do R1 of the t value I found. Now that's 1. So that happens to be negative 1 plus 2, that's 1. 5 plus 3, that's 8. Negative 2 times 1 is negative 2. So R1 of 1 is 1, 8, negative 2. and then R2 of 1. Again, I would put whatever my S value is in here. This does not have to be the same as the T value, but it worked out to be in this case. So now R2 of 1 is 3 minus 2, that's 1. Negative 1 plus 9, that's 8. 4 minus 6, that's negative 2. So you know here I got the same answer, and that means that 1, 8, negative 2 as a point is on both lines. And so these two lines are in fact intersecting. Okay, so that point 1, 8, negative 2 is on both lines. And if you go down here, look at the picture, you rotate this around, you can see like sort of there's this intersection point here, and that would be that 1, 8, negative 2 here. One of the lines is the red line, the other is the blue line. So they're sort of intersecting. What that's going to mean later on is there's actually a plane that you could extend out. Like for instance, here I could sort of chop down, and I chop that with a plane. Okay, so that ends our first worksheet dealing with equations of lines.